Hello, I'm Andy Briggs, and welcome to the amazing Astronomical Alphabet, a weekly programme in which my Astro Radio co-presenter Daz and I will be talking about anything astronomy related which begins with the week's letter of the alphabet. We'll each choose some things to talk about which are in some way related to the universe, but neither of us will know what the other has chosen. We will then reveal facts about them which are weird, strange, bizarre, or simply interesting. Well, welcome, dear listeners, to the amazing Astronomical Alphabet with me. How are you, Daz?
I'm fine, thank you very much.
Good.
How are you?
Good. Are you ready to scale the twin peaks of the letter M, as it were?
Yes, well, I certainly am the spiky one.
Yeah, absolutely.
As I like to call it. So
yes.
And you wouldn't like to drive over
letter.
a lot of those in your cars. Yeah.
Quite an interesting letter as well.
Yeah, yes, that's what I found.
So we'll make a start then. So
yeah, you're first.
I'm first. Okay. So M is for, and this is a double M actually, magnetic monopoles.
Okay, good. That's a good one.
Yeah. Have you heard of magnetic monopoles, Daz?
I have. That's a good one.
Yeah. Have you heard of magnetic monopoles, Daz?
I have heard of them, but you have to explain exactly what they are. Aren't they just got one pole?
Yes, that's correct. Yeah. They are a hypothetical particle which has never been confirmed that it actually exists. So the first research into it, if you like, came actually in the 19th century. So it goes back a long while. And what is a magnetic monopole? It's a particle that has never yet been detected, but theoretically could exist. Now, to illustrate this, if you take a normal magnet, which has got a north pole and a south pole, and you break it into two, what do you end up with, Daz?
Two magnets with both with a south and a north pole.
Absolutely. So you can never have a magnet that's just got one pole. If you take a normal magnet and break it in two, you do indeed, as Daz says, get two magnets, each of which has got a south and a north pole. If you then break that in two, you get the same thing ad infinitum. It's not possible for a magnet to exist without the two poles. And the other thing, field strength at either pole of differing strengths. The field strength at either pole is always identical. So that's the characteristics of a normal magnet. A magnetic monopole is a hypothetical particle that just has one magnetic pole. It doesn't have the other. If they exist, they're believed to have been created after the inflationary period at the beginning of the universe. And why they have to exist? Well, they don't have to exist, but you know, physicists, whenever there's a case of something could exist, they're in there. Whenever there's a case of something could exist, they're in there. We'll research that to see whether it actually does. So it is, if you like, a bit of a scientific curiosity. And even if they do exist, they don't have any practical use. You can't really put them to any use. They've never been detected apart from one event in 1982. By a gentleman called Blas Cabrera Navarro. On February the 14th, 1982, he made a tentative detection of a magnetic monopole, but it's never been seen since. So I think we can stopping scientists looking for these magnetic monopole. At the Large Hadron Collider, there's an experiment called MOEDAL, MOEDAL, and that is currently searching for magnetic monopoles and also large supersymmetric particles, which, of course, as we know, they haven't found yet. And its beginning, when we come to S, is a bit dead in the water these days.
Supersymmetry, I'll leave that to you.
Yeah, okay. So they're searching for them at the Large Hadron Collider so far, but they haven't found anything. But there's a Russian astrophysicist by the name of magnetic fields around black holes are made up of magnetic monopoles. And if this is true, and obviously we don't know yet, he says that they could represent an entry to an Einstein-Rosen bridge. In other words, there have been a number of ideas in recent years that black holes could represent the opening of a warp in space, if you like, a wormhole that would allow you to travel pretty well instantly from one side of the universe to another, or at least end up somewhere else in the universe, if not on the other side of it. But that's what Professor Novikov claims, that the magnetic fields around black holes are made up of magnetic monopoles. So that will be interesting. And of course, we're learning a lot about the magnetic field around a black hole thanks to that new image from the Event Horizon Telescope of the black hole in the middle of M87, where they realized that the light was polarized and that it was showing them where the magnetic field was and sort of what it was doing. So we're beginning to learn a lot more. Once the Event Horizon Telescope takes images of more black holes, I'm sure we'll learn an awful lot about the magnetic fields of black holes, and we'll see if Professor Novikov is right. Yeah. So there you are. So that was it, really. Quite a short one, but
yeah. Well, the thing is, I mean, we know that black holes are links to other places in space.
Must be true, then. It must be true.
Yeah, it must be true. So they do it. So yeah. No. So why do they think these monopoles, magnetic poles, actually exist?
Well, this is something that I haven't really managed to get to the bottom of. Yeah. But I think it's a case of they merge out of.
Okay.
But as I said, they don't really have any practical use. Although, if they are related to black holes, and they could have
yeah,
they're great scientific value. But as far as we know, they don't exist. So, it's a case of what physicists are like. It's a case of what physicists are like.
Yeah, that's right.
They
think it might exist.
They think it might exist, so they go looking for it. I mean, that's how science works. Yeah,
they'll go to their deathbed still thinking it exists, even though.
Absolutely, and don't forget, anything that isn't expressly forbidden by the laws. And don't forget, anything that isn't expressly forbidden by the laws of physics can exist.
Exactly, somewhere, yeah.
So
it's just fascinating. It's and it could be the link that we need for a Rosen bridge. Yeah,
absolutely.
Exactly.
It could be interesting stuff.
Then actually, mine is a shortish one,
right?
But this describes us, mate. This really describes.
Oh, does it? And what's that?
And
morons.
M is for machos.
Oh, machos.
Yeah, macho man.
As in massively
and now over to you, Andy, again. So basically what these things are is that we all know that dark matter exists in some form, but what this actual stuff is, we do not know. And of course we're looking for things like WIMPs and things which are weakly interacting massive particles, but there is a second theory where you've got this, basically it's baryonic matter, but we can't see it.
Right.
I'll just give you a little rundown on that. It says astronomers have plenty, but what the heck is the stuff anyway? Broadly speaking, astronomers divide the possible kinds of dark matter into two classes: baryonic dark matter and oddball dark matter.
Oddball.
Yeah, must be a technical term. Some dark matter may consist of the same stuff that the sun, planets, and us are made of. This kind of dark matter would be part of a family known as baryons, a class of elementary particles that includes the protons and neutrons found in the nuclei of atoms. The protons and neutrons found in the nuclei of atoms.
Normal stuff.
But it's not the cold dark matter that everybody's looking for.
Right.
Baryonic matter includes all hard to see material that's made of known kinds of matter, including asteroids, brown dwarfs, and white dwarfs.
Yeah.
Scientists can detect asteroids in our solar system and white dwarfs and brown dwarfs nearby in the Milky Way. But far out in the galactic halo, these objects may be under equipment. According to one theory, such hypothetical objects called machos, as you said, massive compact halo objects, could account for dark matter halos surrounding individual galaxies if machos are there in sufficient numbers to account for the dark halo of the Milky Way. So they probably don't make up the dark matter in other galaxies either. So as I said, basically you've got the oddball dark matter, which is what everybody's looking for, the Holy Grail. But then again, everybody's looking for the Holy Grail. But then again, they're saying it could be just normal baryonic matter of things that we can't actually see. So basically, it says because machos aren't microscopic like WIMPs, looking for them is easier. The prime method microscopic like WIMPs, looking for them is easier. The prime method takes advantage of a mind-bending concept from Einstein's general theory of relativity.
Oh, yeah.
To wit, mass distorts the fabric of space and the path of a light wave. This, which means that the mass of the line of sight between Earth and a distant star focuses the light from that star, briefly making it appear brighter. The more massive the object, in this case a macho, the brighter the star appears. In effect, the macho acts as a miniature gravitation and brightening the light from the background star.
Right.
To search for machos, astronomers monitor simultaneously the brightness of vast numbers of stars in the Milky Way's nearest neighbors, the Large Magellanic Cloud galaxy. I'm always a bit dubious about that because there are closer to us in our local group, but we don't see them so well because they're being absorbed by the Milky Way. So
yeah,
we'll stick with it that it's the closest for us.
Yeah.
To reach Earth, starlight from the Large Magellanic Cloud must pass through the halo of the Milky Way, and machos that measurable effect on that light. The searchers record occasional events in which one star or another in the Large Magellanic Cloud seems to brighten unexpectedly and then fade again, as though it was gravitationally lensed by the mass of a macho passing in front of it, and located in the halo of the Milky Way. But the frequency with which these events occur is so small that there can't be enough machos, whatever they are, to account for any significant part of the dark matter in the galactic halo. Presumably, the same is true of the dark matter in the galactic halo. Presumably, the same is true of the dark matter in halos of other galaxies. So that's what the machos are. They're basically they're solid stuff. They're not invisible. They're not. It's just that we can't see them because they are so dim and they're so small. And they sit so dim and they're so small. And they sit in the galactic halo, which is we normally call a dark matter halo, which gives it the galaxy its extra mass to account for the movement of
there's not enough of it to
mass to give us to quantify the sightings that we are looking at.
Right. Yeah, that makes sense. Yeah, because if there were, we'd see a lot of lensing events.
Yeah.
So that's interesting because this thing about dark matter as an attempt to find the missing mass. Now, the fact is that the mass isn't missing. We know exactly where it is. We know where the dark matter is. We just don't know what it is. So I see this so often. Dark matter, the missing mass of the universe, is not missing at all. We know exactly where it is.
The mass is there. Yeah.
Yeah, we know where it is. It's not missing at all. We know exactly where it is.
The mass is there. Yeah.
Yeah, we know where it is. We have maps of it now, for God's sake. So we know exactly where it is. We just don't know what it is. Yeah. But even if you took all of the mass of all the black holes in the universe that are presumed to exist, even if in a worst case scenario, there's still not nearly enough mass locked up in black holes to account for the dark matter. So it's we've talked about this before, but it's it's highly likely, and it's something that we just can't detect because it doesn't interact with electromagnetic radiation. It only interacts with baryonic matter gravitationally. So there we are.
Yeah, of course. You've also got MONDS, which is modified.
Yeah, that's right.
Dynamics, which they say can explain some of the.
Can't explain galactic clusters and things like this.
Yeah, exactly. So,
very good. So machos, and I have to point out, as regards your earlier comment, I would never describe myself in any way, shape, or form as a macho.
Well, the only way I'm a macho is I'm rotund.
Right.
I'm so rotund that I bend light. So
you're not rotund. You're just vertically challenged.
Exactly. That's what I say. I say it's genetic. I said for my weight, I should be 6'7".
Yeah.
So it's my bones haven't grown long enough. So
no, absolutely.
So I'm not obese. My bones haven't grown long enough. So
no, absolutely.
So I'm not obese. I'm undershort.
Yeah, exactly. You weren't dropped on your head as a baby or anything, were you? No.
Well, actually, we won't go into that. It's I wasn't actually dropped.
Interesting.
No, I wasn't dropped on. I was when I was I didn't like going to school, and I was described as having sort of like a soft skull, and I found it very easy to knock myself out. So when I was sent to school, I would sit there and they used to send me home, and our mum said, "Don't, just take him back; he'll recover."
Yeah.
Yeah, it explains a lot, actually.
Why do I find all this so easy to believe?
Exactly. Oh dear, I shouldn't be wearing a crash armor. But no, it's of course, because I was unconscious.
Well, exactly. And how often did you do this?
I used to do it for about the first 2 or 3 weeks when I went to school. This is when I was at infant school. Yeah, I used to do, obviously, so I could get sent home. But in our mum, in the end, they just realised that I was just playing up, and they just chucked me in. And
so you are literally a headbanger.
Yes, exactly. It explains a lot. It explains a lot. What sort of music I like.
Absolutely.
Yeah.
M is for magnetar. Let's just explain magnetars. Magnetars are a type of neutron star. A massive star, as in a lot of mass, after a supernova explosion. It's basically the remnant, the core, if you like, of the star, which is compressed to ridiculous densities. And a magnetar is a type of neutron star. Now, the thing that characterizes a magnetar, as its name suggests, is that it has a really strong magnetic field. In fact, the magnetic field of a magnetar is about 1,000 trillion times stronger than the Earth's. It's 1 trillion times stronger than the Earth's. If you put a magnetar at the distance of our moon, it could pull the keys out of your pocket with a magnetic field. So it has this intensely strong magnetic field. And the magnetars generate gamma rays. And some of these, at least, are believed to come from so-called starquakes, when that magnetic field puts such a stress on the surface of the magnetar that the surface breaks, basically, and has a starquake. And these starquakes could mean that the surface, a millimeter shifting on the surface of a magnetar, is enough to generate huge bursts of X-rays and gamma rays.
Well, they got huge mass, haven't they?
Well, they have, exactly. Now, magnetars are probably about 20 kilometers across, or 12 miles. They have a mass of about 1.4 solar masses. So if you can imagine something nearly 1.5 times the mass of our sun compressed into a sphere that's only 12 miles across, you get an idea of the density. And just to give you an idea of some of that, if you were to take a spoon, well, because it's a type of neutron star, it would take a spoon. Well, because it's a type of neutron star, it will be the same. But basically, a tablespoonful of material from a neutron star or a magnetar would weigh over 100 million tons. So if you can imagine that. Now, the other thing that sets now the other thing that sets them apart from normal neutron stars is that they rotate more slowly, whereas a typical neutron star might rotate 1 to 10 times per second. Most magnetars rotate once every 2 to 10 seconds. Magnetars rotate once every 2 to 10 seconds. So they actually rotate slower than normal neutron stars. Why they have this intense magnetic field is not known. We don't know why some neutron stars, and it's only a minority, turn into magnetars. In fact, only 24 magnetars in total have been detected so far. So they are quite a rare animal. And they are probably, apart from black holes, the most dangerous things in the universe. Your body would just disintegrate because the magnetic field would interfere with the molecular bonds holding your body together, and your body would just basically vaporize. It would cease to exist. So they are really nasty. But because of this thing that's very rare, but they don't stay magnetars forever. This is the interesting thing. Their magnetic fields decay after about 10,000 years, and the activity ceases, the gamma ray emissions cease, the X-ray emissions cease. And given the number that we found today, estimates are that there could be maybe 30 million X magnetars in our Milky Way galaxy alone that will have the appearance of normal neutron stars. So that's quite neutron stars. So that's quite interesting. Yeah. The other thing about magnetars is that they are a strong candidate for at least some of the fast radio bursts that we've detected. These are millisecond bursts of radio energy coming at us from the incredible energy, unheard of levels of energy. And we don't know what they are. Some of these FRBs repeat, some of them don't. The ones that do repeat either repeat regularly or in a quite chaotic, unpredictable pattern. And it's thought that at least, back in about easily 20 years ago, back in the late 90s, I think, or mid 90s, about 20 years ago, the first fast radio bursts were discovered. And we still don't know what they are. It's thought that magnetars cannot account for all of the fast radio bursts because they are such different natures. And there are some weird fast radio bursts out there. One in particular that is just bizarre. But just a little while ago, a few months ago, it was announced that a fast radio burst had been detected for the first time coming from within our own Milky Way galaxy. And they tracked it down to a magnetar. So we know definitely that magnetars can cause these fast radio bursts, but they're unlikely to be responsible for all of them. They come from different phenomena in the universe, but we don't know what the other things could be. X-ray binaries have been suggested. That was a strong contender for an FRB for a while, where you have a super dense star, a neutron star or a white dwarf pulling material off a companion star, generating huge amounts of X-rays. They're not coming from X-ray binaries, so we don't know the cause of them. But because we don't know that much about magnetars, there might be different varieties of magnetars. We've only found 24 of them in total. There might be other classes of magnetar that might explain the difference in the fast radio bursts.
Yes, they're very strange beasts, aren't they?
I
didn't realize they actually decayed. Well, if they come down to a basic standard neutral star, do they actually spin faster then, or do they just stay?
I'm going to go out on a limb here. I would think that their spin must accelerate, because I think I'm right in saying that it's the magnetic field that is slowing them down. stopping them rotating as fast as normal neutron stars. So if the magnetic field decays, you would expect them to spin up as it were.
Yes.
So one thing we could look for, therefore, would be a neutron star whose rotation rate is increasing.
Yeah.
Or magnetar whose rotation rate is increasing, and then we'll know. Or magnetar whose rotation rate is increasing, and then we'll know.
Makes you wonder how many of the neutron stars that we actually see were once magnetars.
Were once magnetars, indeed.
Yeah, exactly. So fascinating, isn't it?
You know, I mean, this is purely my own thought, that perhaps all neutron stars go through a magnetar. All neutron stars go through a magnetar phase in their youth. But can that be true? Because, well, maybe it is true, because we've seen neutron stars, but neutron stars, of course, are very difficult to date as to exactly how long they've been neutron stars. Supernova remnant, the remains of a supernova explosion, then, you know, we have no way of knowing how old they are. So we do know definitively that there's only one way to produce a neutron star, and that's through a supernova explosion.
Yeah.
But, you know, at least for some. So, yeah, interesting, eh?
Yeah, it could be added to the life cycle. Yeah.
Yeah.
This is sort of like, we've always got to have an astronomer, and we've got a bit of a history lesson.
Absolutely. So give us a history lesson.
This is my M is for Reverend John Michel. Well, it's no, he's English.
Oh, right.
But it's, I think it would possibly be a derivative of Mitchell, but they've missed the T out. So
right, okay.
So I call him Michel. Now we're gonna do. So I call him Michel. Now we're gonna do a bit of black hole history.
Brilliant
history here. So I'll just read you what it says here. Physical entities resembling black holes were imagined centuries before Einstein and others profoundly profoundly changed our understanding of space and time. The principal thinkers who imagined dark stars that resemble black holes were John Mitchell and Pierre Simon Laplace. Starting back. So basically, in the 18th century, some of the ideas behind black holes were beginning to be formulated, and in particular, the idea of what is called a dark star. The person who first made the imaginative leap was a very much a product of Reverend, and he had friends, because I'm just looking at a blue plaque here. He was 1724 to 1793, so he was quite long lived.
Right.
And it's a blue plaque that I assume it's at Thornhill Vicarage, and it says yes, FRS, geologist and astronomer. He was rector of Thornhill in 1767 to 1793. He experimented on magnetism and astronomy, also making a torsion balance to weigh the world. His visitors here, William Herschel, Joseph Priestley, and John Smeaton. So he had some really.
Oh, he was in good company, wasn't he?
Yeah, he certainly was. So let's find out a little bit about this chap. So John Michel, the Georgian era was in England a time of relative peace. The English Civil War was long in the past, and England had become a land of relative domestic tranquility. The rise of Napoleonic France was still some way off. Like his father before him, the Reverend John Michel received a university education and entered the Church of England as a rector at Thornhill, West Yorkshire. Mitchell was able to continue his scientific research, following up his interest in geology, magnetism, gravity, and astronomy. In common with other scientists working in England at the time, such as the astronomer William Herschel and the physicist Henry Cavendish, who was a personal friend, Michel, I keep calling him Mitchell, Michel was able to ride the wave of the new Newtonian thinking in which the universe was perceived, formulating his law of gravitation, which explains the orbits of the planets in the solar system as being due to the same force that caused his famous apple to drop from the tree.
Right, I see.
Newton's ideas allowed the universe to be studied using mathematics, and this fresh breed of scientists was able to deploy this novel worldview into different fields. Michel was particularly concerned to use the Newtonian thinking to estimate the distance of nearby stars by using measurements of the light they emitted. He came up with various schemes to do this by relating a star's brightness to its color. So, of course, we know that is actually true. So the color of the star gives us an idea of its temperature.
Absolutely.
And what's happening there. And I've lost my place. To star's brightness. He also considered binary stars, pairs of stars gravitationally bound to one another, and how their orbital motions could give useful dynamical in how stars tend to cluster in particular areas of the sky, testing this against a random distribution and inferring gravitational clustering. None of these ideas was practical at the time. Few binary stars were known, though Herschel was producing an impressive catalogue of various double objects. And the relationship between the star's brightness and its color turned out not to be quite as Mitchell had thought it was. Nevertheless, Mitchell was straining to do for the wide. Michel was straining to do for the wider universe what Newton had done for the solar. System.
Right.
Allow a scientific rationale and dynamical analysis of observations to provide new information about the properties, masses, and distances of the heavenly bodies.
Because I suppose, then
of the heavenly bodies.
Because I suppose, then astronomers had no idea whether the physical laws that we see in the solar system applied throughout the universe.
Yes, exactly. Well, of course, remember the universe was the Milky Way.
Absolutely.
So they were looking it wasn't, as we now know, far away.
That's right.
One particular insight that came to Michel followed from the idea that particles of light are, in Michel's word, attracted in the same way, same manner as all other bodies with which we is bearing the same proportion to their vis inertia. By that he meant mass.
Yeah.
Of which there can be no reasonable doubt. Gravitational being, as far as we know, or have any reason to believe, an universal law of nature. Old Englishy style stuff. A law of nature. Such particles emitted from a large star would, he reasoned, be slowed down by the gravitational attraction of a star. Well, we know that's correct. Thus, the starlight reaching Earth would be slower. Newton had shown that light means the principle of refraction.
Yeah.
If starlight was indeed similarly slowed, Mitchell argued that it might be possible to detect this slowing by examining starlight through a prism. The experiment was tried not by Michel, but by the astronomer Royal, the Reverend Dr. Neville Maskelyne.
All right. I don't know him.
Isn't it strange how a lot of these astronomers, old astronomers, were clerical people?
Yeah.
It's something that I've sort of like found, and you would have thought it would have sort of like smacked against what they believed, because we against what they believed, because we knew.
I have on my shelf here. I have a book, A Guide to the Constellations, by a reverend gentleman, Reverend Gill, and that was written in 1905.
Yeah.
And I suspect that were clerics drawn to astronomy because of their religion, by, if you like, trying to investigate the glory of God, as it were. I don't know.
The mathematical roots and stuff like that. So sorry, I'll just say that again.
Yeah.
Royal Reverend Dr. Neville Maskelyne, who
Right.
looked for the diminishing of the refractability of starlight. Cavendish wrote to Michel to tell him that it didn't work and that there is not much likelihood of finding any stars whose light is sensibly diminished. Chemical speculations required much guessing, and the imponderable was starlight affected by the gravitational attraction of the star from which it is emitted. Michel couldn't be sure, but he was bold enough to make an interesting prediction. If a star was significantly massive, the gravity really did affect the starlight, then the gravitational force could be significant to hold back the particle of light completely, and prevent them from leaving. Such an object would be a dark star. This little-known cleric, writing in his rectory in Yorkshire, had thus been the first person to conceive of a black hole. However, so far of measuring the distances to stars lay in tatters. What was more, his health had been indifferent, and this had stopped him from using his telescope. Cavendish wrote to him a consoling letter. If your health does not allow you to go on with the telescope, I hope it may at least permit the movement of weighing the world. This example of a joke from Cavendish, who was notoriously buttoned up, refers to another idea that Michel had conceived. Weighing the world meant an experiment in which two large lead spheres at the end of a beam or a torsion balance lead spheres.
Right.
So I'll end it there.
Okay.
Instead of Michel's referred to because I know also a lot of the experiments were he did were actually health failed. Cavendish was accredited because being a friend of Cavendish, he used his works and things like that in his own experiments. And of course, a lot of the thoughts that Michel had was accredited to Cavendish in the end. So it's a bit of a shame, but yes, he was a very intelligent chap, and he was the first chap to come up with the idea of a dark star, which is...
I wonder what he'd think today.
Yeah, I often wonder that myself.
Yeah.
You know, what they could possibly achieve with what they could possibly achieve with what because these were out of the box thinkers.
What if you showed him the image of the M87 black hole?
Exactly. What would he think? You know,
well, vindicated. He'd have thought. Yeah. But
his dark star, although it's not actually a star. Well, it could have been a star, although it's not actually a star. Well, it could have been a star originally, but it's the same sort of thing. So the principle was the correct.
And incidentally, in Russia, they're not called black holes.
Oh yeah.
No, they're called frozen stars in Russia, because black holes in Russia. They call them frozen stars in Russia. So that's just something I just sort of throw in there.
Okay then. Right.
Yeah.
Okay then.
Yeah. Okay. Right. Yeah. Back to me, I guess.
It certainly is.
M.
Aurora.
Now I know what you're thinking. It's probably my mother again, saying, if you're stuck for material, get onto the moons of Jupiter, and if that fails, the moons of Saturn.
We said we weren't going to do moons.
And we're not, because it isn't.
Oh, excellent.
And we're not, because it isn't.
Oh, excellent.
Yeah. It sounds like, yes, we did say last week that moon is too obvious for M, so we're not going to do moons this week. Maiasaura is not a moon. Maiasaura was the first dinosaur in space? Interesting, eh?
Oh,
Dinosaur in space. Interesting, eh?
okay.
So Maiasaura was
Didn't
a
think
duck.
NASA was that old.
Yeah. Maiasaura was a duck-billed dinosaur that lived, obviously, I'm not quite sure when, but obviously more than 65 million years ago. I'm not quite sure when, but obviously more than 65 million years ago. And a piece of bone from a baby Maiasaura and a bit of an eggshell from a Maiasaura were taken into space by the astronaut Lauren Acton on an 8-day NASA mission, Space Lab 2, in 1985 on the shuttle.
Okay.
Space Lab 2 in 1985 on the shuttle.
Okay.
And what was the scientific point of doing this, you may ask? What did they hope to find out about the dinosaur by putting it in space? Well, obviously not that dinosaurs had once lived in space, because unless you're one of these mad conspiracy theorists, and it wouldn't surprise me if somebody believes that dinosaurs came from the universe.
Well, the Earth is flat, so they probably fell off the edge.
Ah, that's right. That's right. Like Bigfoot did.
Yeah.
Yeah. You might ask, what did they do with this bit of dinosaur bone and a bit of dinosaur eggshell when they got it into orbit? They didn't do anything with it. So you might ask, well, why would they take a bit of dinosaur bone and a bit of dinosaur eggshell into space? It was purely to say that they'd taken dinosaurs into space. And to be fair, Lauren Acton wanted to do it to inspire children. Because, you know, all kids love dinosaurs. Take a bit of a dinosaur into space to inspire the children. So it had no scientific value whatsoever. It was just an outreach thing, if you like. And they, of course, the bit of bone and the eggshell survived the journey, and they are now in the museum. And they are now in the Museum of the Rockies in a place called Bozeman in Montana, in the States. So you can go and see them there, and that was the first dinosaur in space. So there you
that's
are.
weird. Oh,
Yeah.
that's fun. Well, that's nice though, isn't it? When you think about
it is.
it,
It
to
is.
inspire. I mean, it
is.
inspire. I mean, it would fire up their imaginations, and I think that there could be a children's book in there somewhere.
Absolutely could.
Yeah. Oh, got
definitely.
me mind thinking now. Mind thinking.
Danny
So,
and the Zero-G dinosaurs. Sounds like a roll
in space
or crossroads.
in space. Yeah.
Yeah. There you are. Then.
Intergalactic dinosaurs. Yeah. Right. I am now. My M is for make.
Oh, right.
But it's actually pronounced Makai.
Is it?
Well, Maka. It's better than make.
This sounds like In the Night Garden on the BBC. If you've ever watched that, which unfortunately I had to when I was a few years ago when my daughter was young. Very sad now. She doesn't remember it at all, which is very sad. She doesn't remember the nights when she was laying on, which is very sad. She doesn't remember the nights when she was laying on my chest when she was very tiny, watching it In the Night Garden with me. So, but I'm sure there was a Maka in that. Anyway, I digress. Carry on, please continue.
Right then. Basically, as we know. The International Astronomical Union, having taken the bold but entirely logical step to expel Pluto from the planetary club, the IAU seems immediately to have regretted it and invented not one but two classes for it to belong to. At the 2006 Prague meeting, the newly coined term dwarf planet was defined as a celestial body that is in orbit around the sun, has significant mass for its own gravity to pull it into a round shape, but of its orbit of rubble, and is not a satellite. Determining whether or not shape is nearly round is difficult to do remotely, and controversially to define, but in adopting this definition, the International Astronomical Union gave Pluto, Iris, and Ceres, the largest asteroid, the consolation prize of being called dwarf planets. At the same time, it was acknowledged prize of being called dwarf planets. At the same time, it was acknowledged that other large TNOs, which is trans-Neptunian objects, would be ranked as dwarf planets when they had been adequately measured. And sure enough, in 2008, a Kuiper Belt object named Mackay object named Mackay or Maki, pronounced as 4 syllables, estimated to be about 2/3 the size of Pluto, was judged to pass the shape test and was admitted as the 4th dwarf planet, closely followed by a 5th that was called. The International Astronomical Union seemed to seemingly coming to regret having lumped Pluto like Pluto-like objects in the same category as Ceres, and in the 2008 invented a new term, Plutoid.
Plutoid, I haven't come across that.
Okay.
I thought it was an illness and you get cream for that for the doctor.
Well, that's right, yeah.
If you've got a bad case of Plutoids.
Itchy Plutoids. Plutoid to denote trans-Neptunian dwarf planets. Ceres is thus the only dwarf planet that is not a Plutoid, and there is surely no in that category.
No, probably not.
However, there are probably numerous undiscovered or inadequately documented large trans-Neptunian objects that will join Pluto, Eris, Mackay, and Humanae as both Plutoids and dwarf planets. Incidentally, considering the controversy that caused it, after a classical Greek goddess of discord, whereas Mackay and Humanae are named after Pacific Island fertility deities.
Really?
There you go. Yeah.
Wow.
So Mackay is a trans-Neptunian object, which is a dwarf planet, and it was discovered in 2008.
Well. There you are. Do we know anything about it apart from its sort of rough size and where it is?
Unfortunately, I don't. Unfortunately, I don't.
No.
But they probably do know a bit more about it.
Because at that distance, they're not going to know an awful lot, are they?
No, it's quite a long way out. Hang about. No, I can give you some information. I've just come across a table.
Oh,
all right, here we go then. So what should we have? Right, the name. Right, we'll go with Eris. Diameter is 2,400 kilometers.
Quite big then. Blimey.
The mean distance from the sun is 67.7 astronomical units, and its orbital period is 557 years. It has a known satellite, which is a little moon, called Disonomy.
Wow.
Whereas Maki, so bearing in mind Eris was 2,400, Maki, they've actually got two, it's a guesstimate by the looks of it.
Yeah.
It's 1,300 to 1,900 kilometers in diameter. 45.8 astronomical units from the sun. Diameter. 45.8 astronomical units from the sun. Orbital period is 309.9 years, so 310 years. But it doesn't seem to have any satellites. And just to compare it to Pluto, Pluto is 2,306 kilometers in diameter, with a distance of 39.5 astronomical units, and it takes 24 years to orbit the sun. And of course, it's got Charon, Nix, Hydra, and several other stars.
Yeah. Interesting.
That gives you some idea how it works out. So,
Interesting. Well, there we are. Back to me, I guess. M is for, and I've got another. M is for Maria Mitchell. And Maria Mitchell lived between 1818 and 1889. and she was the first woman professor of astronomy in the United States.
Oh, okay.
And she qualified as a librarian in Powell Keepsy, New York, in 1865. She discovered a comet in 1847. She studied Jupiter and Saturn, photographed many stars, and had lots of astronomical accomplishments to her name, and was made the first professor of astronomy in paid a visit to the Vatican Observatory in Italy, because she was quite famous in astronomical circles, obviously, for being the first woman professor in the US of astronomy. And she visited the Vatican Observatory, and despite everything that she'd done, all her accomplishments, she was told when she got to the Vatican Observatory, she was only allowed to enter it during the day.
Oh,
which for an astronomer is a bit of a handicap. Because why? Because she was a woman, and she wasn't allowed to go in the Vatican Observatory. At night, which obviously these days we think is utterly scandalous. So and she'd also, another accomplishment, she'd been the first woman accepted into the American Academy of Arts and Scientists in 1848. So she got that to her name as well. She was the first woman admitted to the the Association for the Advancement of Science in 1850, and the American Philosophical Society in 1869. She was one of the founders of the American Association for the Advancement of Women in 1873. So she had a lot to her name, but she went to Italy,
exactly.
And the Catholics said, "No, you're a woman, you can't come in the observatory." And the Catholics said, "No, you're a woman, you can't come in the observatory at night."
It's disgusting.
It's unthinkable, isn't it? It's just terrible.
Yeah.
So there you are. So that was poor Maria Mitchell. I mean, you can imagine how she felt, how belittled she felt by the church telling her, "Sorry, you're not allowed in the observatory with the blokes at night." I know.
This is back in the towards the end of the 1800s, you said?
Yeah. So that was when did she go to the Vatican? And it was around 1850, I think, she went to the Vatican.
Things really didn't change that much even after then. They really did it.
No, they
did for a long time.
For a long time, and there's still a long way to go.
They've actually announced. I haven't got the details in front of me, but they've actually announced a new prize for women in astronomy. The Caroline Herschel. Named after Caroline Herschel,
awarding a prize.
Yes, and because she's to a English astronomer or somebody in physics or something like that, we're making a contribution, and the next year it'll be a German thing. It's just sad that they think that there's a need for these things to be brought up to highlight women in science. Thing to it as well, but it's just the fact that we have to do these things just to. I mean, these women. We've said it before. We're not going to.
I mean, it's every time I read about something like this, it just makes me more angry and more angry.
Yeah, exactly.
And determined to do what I can, which is nothing basically, because I just we keep finding these examples, don't we? Going back in history of these terrible miscarriages of justice, if you like. Not in a legal sense, but in a scientific sense. Where you get people like Maria Mitchell who discovered such a lot and done such wonderful work, in astronomy, and then some bloke, in the Vatican turns around to her and says, "Oh no, you're not allowed in our observatory at night."
Yeah, but it's a bloke in a dress as well.
It's a bloke in a dress as well, which makes it even worse. How could you take somebody like that seriously in the first place? If you want to wear a dress, mate, set up space. if you want to wear a dress, mate, it says something about you rather than about her. I'm sorry.
Yeah, exactly.
So.
Oh, yeah, it is.
I think we better move on before
Yeah,
my top really blows. So there we are. Back to you, Daz.
Yes, okay then. Well, we're going. Basically, this is quite a simple one, quite a quick one as well, I think. And it's just called mythology.
Okay.
So
Fine.
the M is for mythology. Cosmology is a relatively new branch of physical science. This is quite a paradoxical state of energy. Are some of the most ancient that humanity has ever posed. Is the universe infinite? Has it been around forever? If not, how did it come into being? Will it ever come to an end? Since prehistoric times, humans have sought to build some kind of conceptual framework for answering questions about the world and their relationship to it. The first such theories or models were myths that we nowadays regard as naive or meaningless. But these primitive speculations demonstrate the importance. We as a species have always attached to thinking about the universe. Today's cosmologists use very different language and symbolism, but the motivation is largely the same as our distant ancestors.
Mm. Mm.
What we need to do is briefly chart the historical development of cosmology, the subject, and explain how some of the key ideas have evolved. And hopefully this will provide other things. So most of the early cosmologies are based on some form of anthropomorphism.
Anthropological.
Yes, so let's go that way.
Yeah.
Anthropological morphosis.
Yeah.
The interpretation of something which is not human in terms of human, of the idea that the physical world is animated by willful beings that can help or hinder mankind. Others that the physical world itself is inanimate, but can be manipulated by a god or gods. Either way, creation myths tend in terms of entities whose motives can be understood at least partly by human beings.
Mm.
There are many differences in creation myths. I mean, we've discussed this before
Sure.
around the world, but there are also some striking similarities. For one thing, their imagery supreme craftsmen. The beauty of the natural world is thus represented as the handiwork of a skilled artisan, examples of which can be found in all cultures. Another recurring image is the growth of or order of from chaos, mirroring the progress of civilization to human society. Yet another parallel is the universe as a biological process. The most striking examples of this occur in myths that depict the cosmos as forming from an egg or a seed, which have you mentioned before.
Yes.
The Babylonian version of Genesis, the Enuma Elish, contains these elements. This myth dates from around 1450 BC, but is probably based on some older Sumerian versions.
Mm-hmm.
In its account of creation, the primordial state of disorder is identified from the sea. From the sea emerges a series of gods representing fundamental properties of the world, such as the sky. Two of these deities, Marduk and Tiamat, fight, and Tiamat, the sea goddess, is killed. Marduk makes the earth from her body.
Of course, as you do.
Yeah, as you do. Yeah. China also furnishes interesting illustration. One involves in this story, the cosmos begins as a giant egg. The giant slept inside the egg for thousands of years before he awoke and broke free, shattering the egg in the process. Some parts of the egg, the lighter and purer bits, rose up to form the heavens, while the heavier impure.
Isn't it? Always
Yes,
eggs.
it always gets these eggs and all that.
Yeah.
And Pangu held up the heavens with his hands while his feet rested on the earth. As the heavens drifted higher, the giant grew taller to keep them in contact with the earth. Eventually, Pangu died, but his body part were put to good use. His left eye became the sun, his right eye the moon, his sweat became rain, his hair and the plants and the earth, and his bones the rocks. There are many creation legends, as have been cultures. There are many creation legends, as have been cultures. And as we know, we've touched on these before.
Yeah, we've talked about a few of them before.
Yeah, African, Asian, European, and American, they all have their own stories, and they're really fascinating. It's to think how these own stories, and they're really fascinating. It's to think how these people thought of the skies and the heavens and the stories that they saw in them.
I know, it's amazing, isn't it?
It's amazing. So
and
a lot of it's been lost.
And again, what they would make of what we believe today about the universe.
Yeah. So I find the mythology really fascinating. But of course, and I think it said in there somewhere that we're basically based more around the Greek mythology. But with people becoming more and more aware of indigenous people's writings and stories, still today. But they can only be told at certain times of the year. So to tell a winter story in the spring would be considered sort of like blasphemy.
Yeah, that's right. That's right.
So and heretical. So yes, and you've got to respect these stories, and
you have to. It's part of everybody's. You have to. It's part of everybody's common heritage.
Exactly.
We have to preserve them. They're very important.
I love the stories.
Yeah,
and of course we've got them with the constellations as well. So
yeah, definitely. I'm sure we'll come back to those as well. M is for Mutnik. We'll come back to those as well. M is for Mutnik.
Mutnik.
Yes, these were the term. This is the term that people used for the dogs that the Soviets sent up on Sputnik missions. Mutniks.
Oh yeah,
they were known as Mutniks. Between 1958 and 1961, the USSR sent 13 dogs into space. Did you know that? In preparation for future missions. The most famous dog, of course, was Laika, who you talked about a few weeks ago. She was launched into space on Sputnik 2 on November the 3rd, 1957. Do you know what Laika...
I probably do, because I've spoken with it before, but go on then, tell me.
It's a very prosaic meaning. Laika means barker.
No, I didn't know that. Sorry.
So to distinguish that from Meowka, which were the cat. Well, I don't think they sent any cats into space.
No, I know the French did. Yeah, I think it was.
Yeah, the French did. That's right.
Sophia.
Yeah. But Laika means barker in Russian. So
okay then.
They knew exactly what they were getting. So
because she was trained along with two other dogs, and because she was trained along with two other dogs, and the method of training was very basic, very interesting. But yes, because wasn't it Kennedy who coined the phrase Mutnik? Coined the phrase Mutnik.
Could have been.
Because I know they gave, I think, because they gave some dogs, some puppies to his wife or his children,
right?
And they were, right. And he referred to them as Mutniks. So I'm sure that's where the name came from. So
it could well have been. Could well have been Kennedy. Yeah, so there we are. So that was it, really. Very short one, but it just made me laugh for the fact that they call them Mutniks, and also that Laika means barker in Russian.
So, short one.
Well, I can step in if you haven't. I've got another very short one here.
Well, I've got a moon.
Oh yeah, no. This is a moon-free zone today.
No, the other ones I've got are quite involved and quite long. So
okay.
If you can step in, that would be great.
Yeah, we just have one more to finish then.
Yeah.
This is my
great.
Yeah, we just have one more to finish then.
Yeah.
This is my last one. M is for a bit of a cheat because it's on the surname again. M is for Johann Muller. But he was also known as Johann Regiomontanus.
Oh, okay.
He lived from 1436 to 14.
Oh, okay.
He lived from 1436 to 1476. He was a German astronomer and a mathematician. He studied trigonometry, but he's mainly known for translating Ptolemy's Almagest. Do you remember the first real map from Ptolemy? He was responsible for translating it from the original Greek into German, and because nobody had done that before. And it had an quite unintended effect. Because it had been translated into German, more people read it, and they said that the Earth was at the center of the universe and everything revolved around it. And people who were educated in Germany realized that this couldn't possibly be the case. So it really helped to overthrow the idea of the Ptolemaic universe, which was prevalent up until the end of the 15th century, really. So spherical trigonometry, and he observed the moon, the motions of the planets, comets, and there is a crater named after him on the moon called Regiomontanus, and it's 108 kilometers in diameter, and it's at latitude minus 28.3. Mr. Muller, otherwise known as Regiomontanus. So there you are. Man. So. Yeah. He was, a big contributor towards getting the idea of the Ptolemaic Earth-centric universe overthrown in the 16th century. So,
by
translating Ptolemy's Almagest,
people realise how incorrect it was.
Because if you look how many academics there were in Germany at that time, I mean, we could reel off loads of names from that period. And the Germans said, "Hang on a minute, this can't be right because our observations show otherwise."
Yeah.
So that helped build the tide. Yeah. So that helped build the tide of informed opinion against the Ptolemaic system. So there you are. Yeah. So that's it then. That's fantastic. That's Mr. Muller.
Yeah.
So another person that's not.
Yes, I must admit I am.
That's not.
Yes, I must admit I haven't heard of that chap.
No, and another person who did great things in history but has been largely forgotten, except by Wikipedia, it would seem. So
good old Wikipedia.
Good old Wikipedia. Yeah. I mean, I always check. I think you can pretty much rely on Wikipedia. I know that it's not perfect because nothing is ever perfect, but it's a good thing for checking facts.
Yeah. I've got one very, very quick one for you.
Go on then. M is for.
M is for, if I was to call you a Messiophile, would you be offended?
Does that mean I'm a fan of Charles Messier?
Yes, of course it is.
I've got his picture on my wall. I used to have the Osmonds, but it's now Charles Messier.
Oh, dear.
David Cassidy as well.
Yeah, David Gordon Bennett, you had a sad life. A Messiophile.
That was my sister's wall, I hasten to add.
Oh, okay then.
That was my sister's wall, I hasten to add.
Oh, okay then.
I had Hawkwind on my wall.
That's better. That's better. Yeah, that's more like it. Messiophile is an organism that grows best in a moderate temperature, neither too hot nor too cold, with an optimum growth range from 20 to 45 degrees C. With an optimum growth range from 20 to 45 degrees C, which is 68 to 113 degrees Fahrenheit. The term is mainly applied to microorganisms. Organisms that prefer extreme environments are known as extremophiles. Messiophiles have diverse classifications belonging to two domains, bacteria or archaea, and to kingdom fungi of domain Euchara.
Right.
Messiophiles belonging to the domain bacteria gram-positive or gram-negative, whatever that means. Oxygen requirements from messiophils can be aerobic or anaerobic, and they can contain three shapes of messiophiles, which is Cocos, Bacillus, and Spiral. You find basically everything that make us, who live on us, or live in our stomachs and all that. They are all mesophiles because they all thrive in temperatures which are basically in the middle.
I see.
Mesophiles are opposite to cold environments, are termed psychophilic.
Right.
Those preferring warmer temperatures are termed thermophilic or thermotropic, and those thriving in extreme hot environments are hyperthermophilic.
Wow.
And they can, messing with their genomes, you can actually change what temperatures they thrive at.
Really?
Yeah. So it's so basically it's just a bit of a biology lesson. It says here, due to the less stable structure of mesophiles, it has reduced flexibility for protein synthesis. Mesophiles, it has reduced flexibility for protein synthesis. Mesophiles are not able to synthesize proteins in low temperatures. It is more sensitive to temperature changes, and the fatty acid composition of the membrane does not allow for as much fluidity. The fatty acid composition of the membrane does not allow for as much fluidity.
Right.
Increasing the optimal temperature to 37 degrees C leads to a gradual decrease in protein synthesis. Cold-induced proteins, CIPS, that's CIPS, are which then allow cold shock proteins, which is CSPS, to synthesize. The shift back to optimal temperature sees an increase, indicating that mesophiles are highly dependent on temperature. Oxygen availability also affects the microorganism. But just so basically, we are mesophiles.
We are mesophiles. Well, that's good to know.
Yes.
That's good.
Yes, whereas tardigrades, they cover the whole spectrum.
That's a good chat-up line at a party, isn't it, really? Hello, do you know I'm a mesophile?
Yeah, slap.
Yeah, exactly. Yeah, I'll have to exactly. Yeah, I'll have to
that's my
remember
way of
that
getting beat up. Yeah.
Yeah. Well, I'll try that. I'll try anything. Nothing else.
So
has
desperate.
Worked. Yeah,
so
nothing
desperate.
else has worked. That's a new one. Hello, I'm a mesophile. Nice to meet you. Slap. I'll get my coat. Slap. I'll get my coat.
If you had a chance to get the coat, you're right through the window, mate.
Yeah, and it's closed. All right then. Well, we'll draw things to a close here. Thank you, listeners, for listening to another edition of the Amazing Astronomical Alphabet. It's been great for today, Daz, hasn't it? It's been
it's been a few chuckles, yeah.
Been a few chuckles along the way, which is what life's all about. We will, of course, return next week with more amazing things from the Amazing Astronomical Alphabet. So we hope to edify, entertain, and perhaps educate you again next week. So do tune in again next week. If you'd like to email, whatever, death threats, ransom demands, anything like that, then please do email me at andy@astroradio.earth, and we'd love to hear from you. Anything you want to say. So there you are. Have a great week. Take care of each other. Stay safe. And we'll speak to you again next week. And
says everybody, please stay safe, take care of each other, and we'll see you all again next week for N.
Oh, it's N next week. Now that's going to be interesting. Can we, like we precluded moons for M?
Don't get rid of Neptune.
I was going to say, unless, of course, you discover anything amazing, interesting, or bizarre.
Well, the crisis has been solved, isn't it? We had that the other day. So,
well, that's true.
Great crisis. So
so that's
talk
true.
About that now.
Yeah, we can't talk about that now. But anyway, we'll be back with N next week. Until then, from the Amazing Astronomical.